So let me recall that yes, so let me recall that yesterday we described the derivation of the stream function formulation for the steady two-dimensional water wave problem, so which we have here. So we have a free surface separating water domain with an air domain. So in water we have this semi-linear equation, the delta psi equals gamma psi. And on the water...
Before you begin, I have a question, just to refresh my memory.
Yes.
Maybe this is good for also for...
Please.
So this equation has a vorticity function. It explains if you are irrotational or rotational.
Yes.
But the gamma, in case it is not zero, which is what you do, can be chosen. Explain to me what is chosen in some class. How many gammas can you do?
All. Any possible function. So that the theory works for any... No, you don't need any assumptions. So for example...
Any evidence how in practice, in water waves, there is certain rotational function? Are there any typical gammas in the experimental literature? Sorry for this. Maybe some you have to think about it.
Yeah. So, so this is supposed to describe wave current interaction. So usually in a river with still, well, not still water, water would travel at the same speed at every height. But in some situations, the speed can vary with height, and this is called the shear currents. Yes. And so, and this is, so this is the water surface. And somehow, maybe a disturbance can come from infinity and meet this shear current, and this leads to a wave with the vorticity, with some gamma which is determined by the velocity distribution in this unperturbed flow. So that's the basic idea. And yes, so there is a huge literature, I suppose, on stability of shear flow, so this kind of thing. So usually in fixed domains, but they make sense with free surface as well. And for
Taylor instabilities,
right? Yeah, things like that. Yes, and then also in the literature and the possible singularities in the Euler equations. So vorticity plays the key role with this Bill-Kato-Maida and so on. So, yeah.
Okay.
So it makes, although I mean usually, typically.
But at least your gammas will be smooth functions.
They can be smooth, but they don't have to be. So you can define weak solutions for even for, I think, for bounded gamma, so to say.
Sorry for the interruption.
No, it's a very good question, actually. Yes. And as I said, so it is actually unsatisfactory to prescribe gamma from the beginning, and some people like John Toland have some different ideas which are better of I mean how to describe waves with vorticity, but from the point of view of PDE, so thinking that you have a semi-linear equation, so normally the nonlinearity here will be given, yes? So it makes it easier to prescribe gamma, but in principle the equation that one should solve is just delta psi x psi y equals delta psi y psi x. So, but then, yes, so this is like elliptic with the Laplace. This is not so clear what it means to treat it directly. Okay. Yes.
You got the second equation, I mean, with Laplace without gamma.
Yeah.
by subtracting two equations, not.
Yes.
You eliminate gamma prime.
Yeah, so this is the vorticity formulation of Euler. So vorticity.
So maybe in this subtraction you lost the information.
No. You can go both ways. So people have worked on this. So the idea is that this equation here is almost equivalent to there exists gamma such that. So if the gradient of psi was not zero, then at least locally they have so delta psi and psi have the same level sets. So delta psi is a function of psi. Okay. So this is the 2D problem, and so this is Bernoulli condition. G is the gravitational constant 9.8 or whatever, and this Q can be anything, but by just by vertical translation we can arrange that Q equals 0, because we are free to choose the origin of the coordinate axis as we like, and we can also normalize. Instead of G, we can put 1/2 by scaling, so to get rid of unnecessary constants. So now I will start by, so I will describe the three-dimensional axisymmetric problem in less detail than the 2D problem, and then study singularities. And for that, I will actually concentrate on this. And so what I'm going to say now is more important than what I said about the 2D problem. Okay, so three-dimensional axisymmetric geometry means that if we have coordinates x, y, z, so the fluid domain is invariant by rotation around the z-axis. So if we have one point in the fluid, and then if we take the circle passing through it, and with the horizontal circle passing through it, and with the center on the axis, so all of these points will also be in the fluid. And so we should imagine that the maybe the free surface is a surface of revolution around the z-axis. Yes, so something like this. You see, sort of see what I mean. We are using cylindrical coordinates for the description. So r, phi, and z, maybe not the most usual notation. So the vertical coordinate remains the same, but the horizontal coordinates we write in polar coordinates. So a point here. So let's say we project it onto the horizontal plane, and then join it to the origin, and the distance to the origin is r, and the angle is phi. Yeah, so this is the setting, and in an axisymmetric flow, so if we take a point somewhere in space, the fluid velocity can be decomposed into a vertical component and a component in the horizontal plane in which that point is situated. And this horizontal component can be decomposed along the radial direction and the direction tangential to the circle. So in the axisymmetric flow, what is specific is that the decomposition in the horizontal plane only has a component in the radial direction. So this bit, the third component of the vector along the circle, is missing. Okay, and so if I take different points on the same horizontal circle like this, so the vertical component of the velocity is the same for all of them, and the component in the radial direction is also has the same length as this one. So the velocity vector is characterized by two scalar quantities. So here r and z are just subscripts, are not partial derivatives. Yes, so the vertical thing is Vz that you can see there, and the this radial component has magnitude Vr and is directed along the radial direction. So it's the same thing multiplied by cos phi and sin phi. Yes, so is that sort of okay? So again, there are so the velocity field is described by two scalar quantities. So this Vr and Vz. So and now, so just like in the two-dimensional problem, the incompressibility ux plus vy equals 0 ensured the existence of a stream function. So it is very well known, and in all fluid dynamics books, that such a vector velocity field can be described by a Stokes stream function. So psi, capital psi, which depends on the so only on the distance to the axis and on the vertical position of the point, so that the two Vr and Vz are given by those formulae there. And so again, the idea is that the 3D Euler system in this special geometry can be reduced to an equation for this function capital psi, and this is what I want to do. And here again I could consider vorticity, but it will, so let's try not to complicate matters unnecessarily. So if you just eliminate the pressure like we did in the 2D problem, so we get this equation for capital psi there. So which is, I mean, so if it did not have this factors 1 over r, so it will be just the Laplacian in these two new variables, but like this it's divergence form elliptic operator with coefficients which are singular on the axis.
And it's very curious that this radial part corresponds to the Laplacian in dimension 0.
Yeah, I noticed.
Write r to the n minus 1, so n equals 0 to get 1. It's very strange. The dimension 0 has this Laplacian. The stream function of this.
Yeah, so maybe there is some connection with the. Okay, and then on the free surface, so again, like in the 2D problem, so it's a zero level set of this function, and then the fact that the pressure has to be constant leads to something very similar to what we had before, but now, so that is the, there should be a 2 here, but it doesn't matter. So just like there, so this is the vertical coordinate equal constant, and this is the velocity. So, but just it has a factor 1 over square in front. So the problem is very similar. But on this, so I think that there are, I have only seen very few papers. So I searched the literature, so maybe 2 or 3 papers. But yeah, definitely something like this is considered in Alt, Caffarelli, and Friedman jet flows with gravity. So they do minimization for a certain energy and so on, and and they prove regularity, yes, away from the axis of symmetry and the set of stagnation points, which are of those of zero gradient. So they are doing the complementary case to what I want to do. So I want to study exactly the singularities, the points on the axis and on the whenever the gradient is 0. Okay, and so
yeah. If you expand that just in the with the derivatives, then you get the Laplacian plus something, the lower order term.
Yes.
So, right.
If
That's the reason keeping in divergence form.
Well, so you still
The new term has 1 over r anyway.
Yeah, but I can multiply with r away from the axis.
well, you will see that no. So I will be using some sort of variational methods here, and the divergence form comes naturally from the critical points of the energy, and yes. So if you just look at this, you can look at as a perturbation of the Laplacian, but then you lose the variational structure.
What monotonicity formula?
Yes. Yes. So and here, yes, for this problem I will just do regularity. So I don't know. I'm not saying anything. Yes, I don't know. I'm not saying what should be the boundary conditions at the. So it will be just maybe a local question and so on. But and while in the 2D problem, it's natural to consider. The water to be below air. So here apparently it makes sense to consider both. So it could. There is actually a paper.
Which direction is the water rolling? I mean, the water there is rolling in which direction?
No, it's so it can either be completely steady. So this does not move. So just water inside moves, but the shape remains the same. What we could imagine this translating in the vertical direction. So because of Galilean invariance, stationary problem is the same as traveling wave problem. And so there is a paper by Garabidian, which is about a bubble rising in a tube. So for him, the setting is you have a cylindrical tube like this, and so what is here is a bubble. Well, so it's an air region, and outside of it there is a water region, and so this thing is extends to minus infinity vertically, and moves along this axis. So people have considered the problem with water above air. Although more naturally, I would imagine the air above water, and for example, I could think of a situation of a. So if we had a swimming pool which is circular, so to say, and so imagine water is completely still on the surface, but then we can start pumping water from below. So introduce like a source star, pumping water and so on, and then so this will take some free surface and so on. So maybe a stationary free surface. So the kind of problem that I am considering here. But as I said, I'm not sure. Yes, I have not found this too often in the applied literature to see what. Yeah, it makes sense. It makes sense mathematically, so to say. Okay. And yes, so in this problem as well, I can take q equals 0 and g equals 1/2. So. So going back to the 2D problem and with the Stokes conjecture. So what is actually the statement, and so what was Stokes' argument and so on. So this setting with well, keep 2gy, let's say with 2gy equals 0. So you see that the because gradient is always positive, so y has to be less or equal than 0. So this free surface is always in the lower half plane, and the gradient is 0 only if the surface touches the axis. Yes, so and then you can translate it horizontally and so on. And let's say that there is a point where the free boundary touches the horizontal axis, and that point is the origin. So Stokes considered this situation, and he assumed that the free surface has a corner, although he did not specify of what size, and that the function has an asymptotic expansion around that point. So he did not say what kind of powers should occur in that asymptotic expansion. And by trying to match the conditions and so on, so he came to the conclusion that the only possibility is that for both Dirichlet and Bernoulli to be satisfied, well, in the zero vorticity case, is that if this was a corner of 120, symmetric, and if the leading term in the asymptotic expansion in polar coordinates would look like this. So where rho is the radius and theta is the angle. So this is essentially the imaginary part of the complex power 3/2. Yeah, so this is a harmonic function. And this is a solution of the... but then, yeah, so easier way to see that, I mean, why this result should be true is that this problem has an explicit solution, which is called Stokes corner flow, where the fluid domain is a wedge, so making symmetric angle of 120 degrees, and the function is exactly that, what I wrote on the above line. So this is some sort of like a global solution of the problem, which should describe, we expect it to describe locally the behavior in a non-trivial wave. But it's completely homogeneous with completely straight free surface. But he assumed all of these kind of things. So while if one wants to give good mathematical proof, so we should have a starting point, some suitable weak solutions. And we should try not to make any assumptions either about the existence of a corner nor on any asymptotic behavior of the stream function. So we want to derive this kind of behavior only from the interplay of the PDE with the two boundary conditions. Yes. So okay. And as a word of caution. So this is something that I worked on in my thesis. So it makes sense to consider a similar free boundary problem, I mean, for a harmonic function, and we keep the zero condition, but replace the Bernoulli thing like this with the gradient of psi being a more general function of y, which is given, so to say. And then the result is that, which is in my thesis and so on, still based on complex analysis methods and so on. So if the function, this nonlinearity, has a power-like behavior, in a sense which I'm not making very clear, so then there has to be this singularity. So if alpha is 1/2, then you get 2 pi over 3 and so on. So this generalizes the Stokes conjecture. But if you allow well, more complicated function, then it is possible to have a free boundary which does not enter the origin under a well-defined angle, but has infinitely many oscillations between maybe two different lines. So the fact that the curve must make this corner is non-trivial, and it depends on the specific on the nonlinearity in the problem. Okay.
So your gamma from the beginning is really not important in this.
It's okay. Yeah, this is a very good question. So it is important when one is trying to when one does global theory of existence of solutions. So it makes all the difference. But for regularity, which is a local question, it makes a very small difference. So I will ignore it for the most part of the talk, and at the end I will make some comments about what happens if we introduce gamma. So it's of much lesser importance for the regularity question. Yeah. Okay. So now we have these two problems, and I will yes.
Is there any approach that one continues psi not by 0 above the surface, but it's 0 in this formulation above the surface?
Well, there isn't anything mentioned about it. I will extend it by 0 indeed on my next slide.
Is there any approach that one extends it such that this condition on the boundary is satisfied on all over above the surface?
I'm not sure whether that would make a lot of sense. So no, I'm not aware of anything. It's seemed most natural to extend it just by 0. I mean, in fluid dynamics, so people actually don't define so the stream function is only defined in the fluid. So in the air, you don't have anything. Yeah. Okay. So let me. So put both the problems in a similar framework, so to say, and so there it is. So in the 2D problem, I will change notation from xy to x1, x2, q equals 0, g equals 1/2, and consider only a local version of the problem. So omega changes, so is no longer the fluid domain, so it's just something small, could be a ball or something, and the inside of it, so I assume this is really small, and then we have a water region and an air region, and definitely this is omega is a neighborhood of the point around which we want to study asymptotics. And so this is what you just said. So at least locally it makes sense to assume that the function has a certain sign. Although globally in the problem this is not justified, but locally we can assume. And then we extend it to the air region by 0. So it is a continuous function across the boundary. So it has a jump in the gradient and so on. So the free boundary now becomes the boundary of the 0 level set. And then, as I said, vorticism is less important here. So let's just look at this. Okay. And now in the 3D axisymmetric problem, so this R and Z, I will again denote them by x1 and x2. Q equals 0, again G equals 1/2. R, the distance to the origin, is always non-negative. So now my functions will only be defined in the right half plane. So R2 plus means that the first coordinate R is greater or equal than 0, and then we have this omega and so on, and maybe somewhere around here the free boundary psi greater than 0, psi equals 0, something like that. And then the equation is this divergence form and so on, and the Bernoulli condition is this. So the difference is this between the two problems is just this weight 1 over x1, both in the operator and in the Bernoulli condition. But so I will devote more attention to this problem. This looks more interesting. Yes, so all of problem involving the Laplacian have been studied very, very much. Okay. And yeah, so what is the general, what is the idea of the general approach that we are using for the study of singularity? So it is as the standard idea in regularity of free boundary problems. So looking at blow up limits, so to say. So so we take a point on the free boundary where psi is 0, and so we try to we look at the rescalings of the function psi in this way. So let's say this is the free boundary point. So this such a transformation has the effect of zooming in closer and closer to the singularity and magnifying things. So for example, if in the 2D problem we did not know what the shape of the curve looked like, but we take this sequence of smaller and smaller balls and magnify things, so make them of size 1, and if in the limit what we see is exactly this Stokes corner flow, so this is the basic idea of our proof of the conjecture. Okay, so the general approach.
They are scalings at free surface.
Yes, yeah. Yeah, I mean, in the interior things are smooth and so on, yeah. So this is something that you can try to do in any problem, and ideally, so you would like to get a unique limit, I mean, general, yeah, that to find the PD, which is satisfied by the limit function, so maybe the same as the original problem or something closely related and maybe easier. And the really important thing is that why should this, in the limit, you should get something better than what we have started with. So, so it would be really good if this limit function was homogeneous of the right degree. Not to get 0 in the limit, because then we would lose all information. And once we establish this, we get back to the original problem. And we need some arguments to infer some conclusions about the general problem. So this, I believe, will be used by the very much in Professor Shagolian talk as well. So this kind of blow-up methods. So to me, yes, so the method, this kind of thing is not new. Of course, maybe 20 or 30 years old. But in these problems that I'm going to present, so the calculation seems a bit more complicated somehow than I have seen in other problems. And then, yeah, so I would say that the application is also important to this problem that has been around for 200 years and so on. So the Stokes conjecture has been proved in the 80s by complex analysis methods and singular integral equations, but giving a proof like this and one which, as I'm going to show, extends to the 3D axisymmetric problem is good. So when you try to do something like this, you ask yourself, okay, what's the most natural alpha to consider? And if the problem has some is invariant under some scaling, which it is in those situations, then that would be a good candidate to start the analysis. So,
possible to go back to just want to say the equation.
Yeah. Okay, but in the axisymmetric problem, so there are actually 4 different kinds of points. So
your equation is degenerate elliptic when you get
yeah, it is, yes. So singularities can occur also there. And so if both coordinates x1 and x2 are not 0, so we are both away from the axis and gradient is non-zero, then we expect smoothness. But whenever either x1 is 0 or x2 is 0, then maybe singularities are possible. But yeah, so the idea is that there are 4 types of possible points. So these are the coordinate axes and so on. So, and a piece of the free boundary. So a point where neither coordinate is 0, and then maybe there could be a point where x2 is 0, but x1 is not 0. And then there could be something where x1 is 0, but x2 is not 0. And then the origin where both coordinates are 0. And then maybe the scaling behavior is different depending on the point we are at. And so you do a sort of a formal.
And the difference of the 2 points which are on the vertical axis.
Sorry, on the vertical axis. So if
There are 2 points. Which is the difference?
So you look at this, and gradient is x1 squared times x2. So it is 0 in both cases, but with a different order somehow.
And this is due to gravity.
Yeah, this term is due to gravity, yes.
And the gravity depends on vertical out.
Yeah, only on the vertical. Gravity acts vertical, yeah. So that's why. So we try to identify some sort of scale exponents for invariant scaling, and at the origin, so the exponent is 5/2. This is fully invariant scaling. So if we have a solution of the problem and we replace it by psi of Rx over R over 5/2, so it is a solution of exactly the same problem. At all the other points, we identify exponents 1, 3/2, 2, and so on. So if we replace psi by these rescale functions, so we don't get solutions of exactly the same equation, but of perturbations which maybe disappear in the limit. Yes, please.
Your scaling are the same, both. I mean, are you taking homogeneous scaling?
Yeah, they are all homogeneous, yes.
Why not anisotropic scaling?
I don't know. Why would I do that?
It's natural for the equation you're dealing with.
Maybe, but I can solve the problem with this. So, well, so this almost
Your equation scales differently in different directions.
it's not quite right. So on the one hand, so this I can preserve at certain points, and at some others, so namely here and here, in the limit I am getting the Laplacian. Yeah, because for example, for a point like this, so x1 behaves like a constant. So this is almost like a Laplacian, and this is like the 2D problem. So well, if you do what you said, well, I mean, it's okay to have the Laplacian and the same operator. I mean, rather than get new PDs which are yeah, anisotropic, so to say.
May I comment something?
Yeah, please.
In connection to Luke's argument. If you expand it, this is the reason I was pushing for expansion of the. Then you get Laplacian equals to something, and then you multiply with x1, so you get the right-hand side that might be 0 or not. And that's already, so to me it seems easier to see when the Laplacian also pushes.
Well, so this has a solution which is homogeneous of degree 5/2 in the exact solution. So to say, I mean, which if you and you can see that from that equation. Well, if you expand the Laplacian and cancel some terms, I'm not. I don't know. So maybe it simplifies, but we did not need that. Okay. So what are the results that I'm aiming to get to? Okay, so here at interior points, so completely interior, this we did not look in details, but things would be expected to be smooth. So gradient is not 0, so standard the theory should apply. And then at a point on the horizontal axis, but different from the origin, so this weight is like close to a constant, so things behave like the two-dimensional problem. So here we do get corners of 120, so like Stokes conjecture, same kind of results. At points here, the only possible behaviors are cusps, so air cusps. So just like in the picture, so this is air cusp pointing downward, but it is also possible to have, so how would that look like? Air cusp pointing upward, so meaning that here is air and here is water, and the double cusps with water on the sides. So it's a bit strange that at such points it's not possible to have a smooth solution. Maybe these cusps are not possible at all, but they are the only things compatible with our blow-up profiles. Okay, and at the origin, which is the most interesting thing somehow, so we get an explicit solution, which we can call Garabedian corner flow or Garabedian pointed bubble. So in which there is indeed a cone, but let me extend it in the other direction and see how it looks in 3 dimensions. But the water is above and the air is below, and this has angle of size approximately 115 like this, and 130 here. So the size is connected to the zeros of the Legendre function, as I'm going to see. But this is an explicit homogeneous solution, so just like exactly like the Stokes corner flow. The strange thing is that the water is above air, and so if one is looking the other way around, so there is no solution which is invariant under the no homogeneous solutions with the scaling, with the invariant scaling of the equation. So okay, I made this observation here. Or we could get 0 in the blow-up limit, and that would be a degenerate point. So do invariant scaling, you get 0. So this would lead to a flat free surface, which is so it can have either air here and water here, or water here and air here. So both these are possible. And in the more interesting case of air above water, so we continue the analysis, and for that situation we derive a new frequency formula, which is so like Almgren's frequency formula, but adapted to the problem that we are studying. And so, and instead of this scaling with the power 5/2, which led us to 0, so we do a different scaling, which we want to ensure that it leads to a non-trivial limit. And the standard scaling in such functions is like this. So we divide it by the weighted L2 norm on the boundary of the ball, and this new blow-up sequence, so we are able to identify a unique blow-up limit. And in the proof of this convergence, we also use a concentration compactness result of Delors. And these are the results, so to say, where I want to get. So so in the 2D problem, as you would expect from all of this, so the invariant scaling is 3/2. So we do this blow up with power 3/2. And as blow up limits either the Stokes corner flow, which is good, or wanted to get, or 0, so which is not good. But in the 0 case, we also have a frequency formula, and depending on the assumptions, the degenerate case can be ruled out or not. But yeah, so my plan is to concentrate on these axisymmetric problems and so on, and so the details of the result and so on are in those 3 papers with Y's that are listed in the references. Yeah, please.
So the asymptotic behavior of the stream function, is it something you assume, or you know, or you derive?
I'm not assuming anything except for a growth condition, something like at the origin that gradient psi square is less or equal than a constant times x1 square x2 or something like that.
So how do you know this?
Well, so in the 2D problem, this can be proved for all the cases where existence is known. So let me say something about the 2D problem. So we have gradient psi square plus 2gy equals 0, and this is the minus the pressure. And by means of maximum principles, so it can be proved that P is greater or equal than 0. So this is sort of, so you look at the same expression and you prove some Bernstein estimates, essentially. So it is 0 on the surface, it has a certain behavior on the bottom, and it is subharmonic or superharmonic. So in the cases of interest, an inequality like this, gradient psi square plus gy, less or equal than 0 everywhere in the fluid, can be proved. So now in this kind of problems, there is no existence theory, so to say. So inequalities like this we are assuming. But it's very mild, so just how the gradient grows, right? So no asymptotic expansion or anything. So just a bound on the gradient. Still quite weak.
Okay, so you assume that the gradient of psi is sort of exists on the boundary.
Well.
What exactly? Because
Sure. The free boundary has to be interpreted. The free boundary condition is interpreted in a weak sense, but in the interior, so in psi greater than 0, the function is smooth. So it has a gradient and so on. And I'm assuming an inequality of the type which on the boundary will be satisfied with equality. Well, even with some constant in front of it. So it is an inequality of the right kind. I mean, otherwise, but this kind of growth from the boundary you deduce at the beginning of every analysis. But here we didn't, so there is no existence theory, so we did not know exactly what to start with. So this is a regularity question. So let's just assume this reasonable bound and see what follows from it. Okay. So now the tools in general that I'm going to use to explain in a simplest possible setting, so are the monotonicity formula and the frequency formula. And how they work can be most easily seen in the case of harmonic functions in 2D. So simplifying everything as much as possible. So take a harmonic function in a certain ball at 0 in R2, and the solution with u0 equals 0. So harmonic function 2D is the real part of analytic function. So it has this power series expansion and so on. So it has this kind of expansion into, I don't know how you want to call this, so trigonometric expansions and so on. This is connected to complex analysis, so Taylor series and so on. And we don't know where the expansion starts. Some could start from 1, but maybe from something else. And we would like to identify the leading order behavior, so this first term in the expansion. So like this. So how could you possibly do that? So one way to do that is to see that if you do this kind of scaling, u of rx over r to the n, it kills all the other terms and you get the a leading order term. More generally, so you can ask, you can look at u of rx over r to the alpha and say what happens for different alphas. So for alpha equals capital N, you get what you have. For alpha bigger, you get 0, and for alpha smaller, the thing is unbounded, I believe. Okay. So one way to capture the capital N is to use this Almgren's frequency formula. So you look at what happens of balls of radius r and so on, and look at the Dirichlet energy divided by the L2 norm with the scaling factor in front. This is a monotone quantity whose limit at 0 is exactly n. Okay, so that's sort of okay. So you can prove it either using explicit representation, but most important thing is that you don't have to, so you can prove it directly. And then on the other hand, so there also exists this family of monotonicity formulas. So, so here they do involve the same quantities. So integral of gradient square, the L2 norm on the boundary with suitable scaling factors in front. So now you play around a little bit with the coefficients. And so if you put alpha in front of it, which you didn't know at the beginning, you get a really nice formula for the derivative of this function, which you see here. So you see that so the right-hand side is always non-negative, right? So it contains a square. And it is 0 exactly for homogeneous functions, because the normal to the, so what we have there is, under the integral, is gradient of u at x times, and then the normal is x over r minus alpha u of x. And this being 0 is exactly the same for smooth functions as u homogeneous of degree alpha. So, so this makes you think that yeah, so such quantities will tell us something about the homogeneity of functions. So if our original function u was exactly homogeneous, so this will make this 0, and the function will be constant. So the function is always increasing and constant exactly for homogeneous functions. And the idea is when you do this blow-up limits and try to apply the same thing, you get, well, this function will be constant, and which will lead to homogeneity. So this is the basic idea. But here, so it's a linear equation, explicit formula, and so on. So everything you can do by hand and so on. But in the free boundary problem that I'm going to speak about, so so there is no asymptotic expansion. The equation is yeah. So even if it is linear, so the free boundary condition is non-linear and so on. So it is a much more complicated problem. So there is no yeah, no reason why you should have asymptotic expansion. But to anticipate a little bit what I'm going to talk tomorrow, so so when you study the behavior at the origin, so we are going to look at these two functionals. So one is the L2 norm on the boundary of a ball weighted with the, and I'm using u instead of psi. So this is a weighted L2 norm. And then instead of Dirichlet energy, so it's this weighted Dirichlet energy plus something involving the characteristic function of the positivity set. And this is the energy of the wave. So it has physical meaning. So actually normalized energy of the wave in a certain ball. And so when I look at a similar combination of rescaled things for this problem, so the derivative is exactly, well, with this weight and so on, but it looks very, very much like what we had just for the harmonic functions. Yes. So yeah, I suppose exactly the same formula, maybe with alpha equals, well, alpha equals 2. Yeah, so you take a combination of a Dirichlet energy plus something involving the characteristic function, something the L2 norm on the boundary, and the derivative of this function is always non-negative and 0 exactly for homogeneous functions. And then when you do blow-ups, you get homogeneous blow-ups. I mean, for anybody who has seen this kind of arguments before, it should be clear how the arguments go. But I will go into details of this tomorrow and the day after tomorrow. So thank you.
Questions? More than the ones we already have. Okay, so this formula, the 5 half, that you find there is the worst case. Is it
So
the
it's,
analysis?
it's at the origin, and 5 half is the invariant scaling. So if you want to seek a homogeneous solution, it will have to be homogeneous of degree 5 halves. Because when you look at the boundary conditions, so for example here, psi homogeneous of degree 5 halves, so gradient 3 halves, so you get 3, and then minus 2, 1. So it's the right, yeah, so exactly the scaling exponent. So that's why I consider 5 halves. Well, and the one that is expected to make everything work, so to say.
So
So it's not surprising that.
So the condition on the free surface is gradient. The length of the gradient is something, but the value of the function is 0. So tangential part is 0.
Absolutely, yes. So this is the same as a Neumann condition. Yeah.
So the difference with obstacle problem is simply that the Neumann thing is 0 for the obstacle problem, and here you have it's equal to something.
Yeah, it's something depending on a spatial position on the, yes. Yeah. And well, we also have this degenerate operator here, but which does.
So I mean, in 2D case, it's close to.
I don't know about the obstacle problem. Yeah, but I mean, it's the same kind of arguments that I think Professor Shagolian will be presenting for obstacle problems.
okay, more questions?
No, that's why I said.
Okay, let's start the speaker.